everybody.
MoNaCo's here.
And Milks is present.
Are you here too and listening to us speak to you?
Seriously, turn it down.
Turn down for what?
Hmm.
On page 27 in our pack, we're going to talk about boiling. We're going to give it a new definition and explore some vapor pressure. And so you know, this is our 7th video out of like 9. So
Almost done.
You're doing what you're supposed to do. You're going to finish the lectures for a unit in 5 days.
Well ahead of time.
Like you're supposed to.
Right. So we can get on to practicing and moving on and assessing.
Beautiful. Beautiful.
Let's do it.
So, how are pressure and boiling point related? And I'm not talking about the pressure of Milks and MoNaCo telling you to watch your homework lectures every day. I'm talking about the pressure, that thing. What am I talking about, Milks?
Ooh, you're talking about force exerted over
Area.
Pressure.
So, it's related to boiling, so we got to define what boiling is. And when I say boiling, most of you are thinking like hot.
True.
It's got to be hot, mister. And
True.
they're thinking about boiling water, right?
That's normally what I do to make noodles. Yeah, I boil water.
I mean, that's when we see boiling in our lives. I mean, what other times do you see anything boil?
Oh, I can't think of any other time I see
Maybe if your
anything boil.
radiator's boiling over because your car's overheating or something like that.
That could bubble. But that boiling is that bubbling.
Bubbling.
And it's literally that transition from liquid to gas. That's what we call the boiling phase, vaporization. Right. So let's redefine it.
Yeah.
Get a little bit more specific.
What exactly is boiling?
Well, it occurs when this thing called the vapor pressure equals this thing called the atmospheric pressure.
I heard about atmospheric pressure, mister, from earth science. That's how much air is pushing down on my head right now.
Correct.
But this vapor pressure?
Well, we're going to have to redefine that, I guess, a little bit too, right?
What's a vapor pressure?
Well, vapor is the gas that is coming off of the top of the liquid.
So like the surface of the puddle turning into a gas, like evaporating, vaporizing?
Correct.
Oh.
Now, if I heat it,
it goes up. It's got it.
Well, I give more energy to the surface molecules to get them to jump into that phase.
So the pressure would go up.
The pressure going up off of the liquid is the vapor pressure.
And so boiling is when that thing that the liquid's doing, going up, turning into a gas, is equal to the atmosphere, which is already a gas,
pushing down. Right.
Oh.
See, if it's not quite equal,
it's not a tug of war, it's a push of war.
Kind of, yeah.
Okay.
See, if that atmospheric pressure is too high, it's going to keep the molecules down.
And keep them in the liquid.
There you go.
They're not going to be able to jump into the gas.
They just don't have enough energy to overcome that force that's pushing down on them.
Right, okay.
So you got to give them
because you got to have energy in order to turn into
and energy is heat. So
you got to
heat the water up
to beat the atmosphere.
Right.
So that's why water boils at 100 degrees, because that's when water's beating the atmosphere.
Water's vapor pressure is equaling or beating the atmospheric pressure.
Oh, okay.
And I really can only do so much about that, but I can change the atmospheric pressure sometimes.
And you'll see.
Yeah, I can't wait to do it. I really can't wait to do it. So, hey, STP, let's talk about that one more time. Standard temperature and pressure.
Always.
It is, again, one atmosphere, 0 centigrade.
Or you might see it as 273 Kelvin and 1 atmosphere.
True. And there's another conversion for our reference table here.
Right.
That 1 atmosphere is also going to equal 101.3 kilopascals.
And a pascal is a unit of pressure.
Yeah, some French guy.
Yeah. And an atmosphere is a unit of pressure.
Correct.
So what you're telling me is that 1 atmosphere equals 101.3 kPa, kind of like 1 dozen equals 12.
Very much so. Like 12 inches equals a foot.
Same amount of pressure, different units.
Correct.
Cool. Let's go. Let's move on. So how do we measure this pressure?
Well, there you go. You tell.
It's a force created when a particle of gas collide with the wall of a container. This is kinetic molecular theory's most basic tenets. When a collision between a gas molecule occurs with the wall of a container, it exerts pressure and force that we measure in different units. We only use atmospheres and kPas, kilopascals, in this course. There is another units, torr for torricelli, another guy, and millimeters of mercury, not for a guy named Mmhug, but for literally
The barometer.
Measuring a stack of mercury liquid in a tube.
Yeah, that's like the weather guy. What he would use to talk about the pressure, low
Barometric pressure.
Yeah, low pressure system, high pressure system.
He's probably working with units of millimeters of mercury or torrs.
Right. And we're not going to get into like pounds per square inch, which is like your tire pressure.
Because that's an English unit,
right? We
not
don't like
an SI unit.
But that's what the one you're going to see probably if you're
in your life.
Yeah, with a tire
down
pressure.
In the automotive shop. Yeah.
Tire
How many
pressure.
PSI am I supposed to put this up to?
Right.
32.
Right. Bike tires.
That's
less,
related
right.
to how the gas collides with the wall of the container.
The more
Pump
gas
it up,
in there,
you're putting more gas molecules
more
in there, more collisions. But that's what pressure is and how we measure it. Kilopascals and torrs with these things called manometers and barometers.
Right.
Moving on.
Here we go. Let's define atmospheric pressure.
Mm-hmm.
This is going to be the pressure created from the weight of the air that is pushing down on you. So I like to think of this this fake column of air. You draw a little halo above your head. That halo forms a cylinder all the way up to the top of the atmosphere.
Like 60 miles high and stuff.
Right. So there's some volume of air that gravity is pulling down on those particles.
And I'm at the bottom of that stack.
It's on
so
your
it's all
head.
squishing me. It's like, it's like putting your thumb under a stack of textbooks.
Right. And then
that's going to be more than 1 atmosphere of pressure, obviously. But
right.
Conceptualizing, you are the thumb. The textbooks above you are the atmosphere pushing down on you.
True. Now let's get into what that vapor pressure is.
This is the thing that is the importance.
And it's something that we may have never heard of before, so that makes it extra complex.
Mm-hmm.
So here we go. The pressure that the vapor exerts as it changes phase from liquid to gas. This is the pushing up. So why don't we draw a quick picture?
Yeah, got to have a picture for this, and I'll put it in here for you. I gotta have a beaker. In this case, it's a nice big one. And that beaker's got a liquid in it. And I'm going to use blue for my liquid.
Okay, yeah, we'll call it water.
I'm not going to do the crazy thing,
Just draw it.
Just like draw the surface of the liquid here.
Okay, good.
Okay?
There's
Water.
my liquid.
H2O, yeah.
The surface of that liquid is going to do what?
It is trying to turn from a liquid into a gas.
Right. So
it's going to vaporize.
And I wrote, right, and it says on the page right below it, it is pushing
upwards.
up. Let's do it.
So there we go. We got these little gas molecules, these water molecules pushing upwards against the atmosphere. And they're always doing this, no matter what temperature the water's at. They're just pushing up.
Right. The colder it is, the
The
smaller
less they push.
the smaller that arrow is going
But
to be.
guess what? Even solid ice has a vapor pressure. It's why it can slowly disappear in your fridge over time. Moving on, we got to look at the vapor pressure.
Oh, wait, let's do the atmosphere coming down.
Atmospheric pushing down. I'll use red for the atmosphere pushing down. So the atmosphere is pushing down all the time.
There we go.
So remember, red, atmosphere, and blue, vapor pressure. So when these are equal, you boil.
Correct.
And when they're not, you're either a liquid or a solid or nothing's really happening. When they're equal, they boil.
Right. So the vapor pressure has got to increase enough to overcome the atmospheric pressure. At boiling, atmospheric pressure equals vapor pressure.
So there I wrote.
That is the new definition.
Atmospheric pressure equals vapor pressure is boiling.
True. New definition.
So we got a bunch of definitions. Let's throw another one.
Yeah, normal boiling point.
Well, normally I'm at 1 atmosphere.
Right. So at standard temperature and pressure,
Which is normal.
Right. What temperature do I boil at? So we
That's
need
what we
that.
call normal.
We need that baseline,
Mhm.
and that baseline pressure just happens to be 1 atmosphere. Now our cold pressure systems, our low pressure systems happen.
Higher and lower pressure.
Very
a little
slight
bit.
changes to that.
Here in Rochester, we're very close to sea level, so we're very close to normal boiling point. When we boil water here, we get 100 degrees Celsius.
Got it.
If you went to Colorado, which is much lower atmospheric pressure,
Right.
the boiling point changes. Or if you go to Death Valley, which is much higher atmospheric pressure.
And so now the boiling point of a liquid is going to change as the pressure exerted on it changes.
So imagine those red arrows I drew up there with our atmosphere getting bigger and smaller.
Correct.
More atmospheric pressure, it beats the vapor pressure, you do not boil.
Right. I'd have to really heat it up to overcome it.
Right. Less atmospheric pressure, the vapor pressure overcomes the atmospheric much easier.
Yeah.
You don't have to heat it much at all.
You know what the beautiful thing is? We got a chart to help us figure that stuff
Let's
out.
check that out.
Check
Here
it.
is our beautiful chart. The point of the background that we've been giving you is
Right.
to learn how to read this chart.
Right.
What
The
it
reason
means.
why we even had to talk about kilopascals, you'll see that it's written there
Right there.
on that dotted line.
And I hate it because this dotted line is not labeled normal boiling point.
That's the piece you got to know.
You got to memorize that 101.3 kPa is normal pressure.
And this is kind of how we read it, right? So if I go across this line of normal boiling point, this normal atmospheric pressure, and I get to the line where water crosses it,
Yep.
and I look down
I can see that's a temperature.
of,
I would assume
Water.
boiling.
it's exactly right.
Right. So this at 101.3 kPa, the vapor pressure of water is the same as atmospheric pressure.
Yeah.
And
These
therefore it
lines, these four lines that you see, they are the boiling point lines.
Right. You don't have this picture, so don't try and draw this in there.
No, but you do have it. You
have
have it in
a
your reference table.
so
And I
this
just
is
want you
what
to know
we're
how.
going to be using.
Yeah, you just need to know how to use it.
Okay.
Okay.
Moving on
So
here,
now,
next
if
one.
I go and raise the pressure, increase the pressure,
Then I look on the curve of the element or the compound. Sorry, the compound that I'm looking
Right.
at.
And
I see
go
now
over
I'm still
water.
talking water, and I trace down. That's like 110 degrees.
so what happened? We raised the pressure, and the boiling point
Rose.
rose.
So if I increase the atmospheric pressure, that dotted line, the vapor pressure needs to increase in order to boil.
Right.
And to get to there, you got to bring it up to 110 degrees. Let's
Right.
see what happens when we drop atmospheric pressure.
If we drop it way, way down,
Yep.
we go and find where it crosses the water line, and look, now we're boiling at like 70 degrees.
Yeah, 70 degrees Celsius. So when the atmospheric pressure is dropped to 30 kilopascals,
Yep.
the vapor pressure, the temperature at which water gets to 30 kilopascals of vapor pressure, where they equal, is 70 degrees.
There you go. That's how we read this.
Cool. So let's see those relationships, like
Okay.
the quick write-downs.
There you go. So first of all, when I am boiling, vapor pressure and atmospheric pressure are the same thing.
On table H. That's
Because-
what the definition of boiling is
Correct.
now.
Correct. So when I go across and I read vapor pressure, if it's asking me what temperature does it boil at, or what pressure does it boil at, there you go.
Mm-hmm.
Right. So it's going to be, if I'm boiling, they're the same. And here's our relationship. So as atmospheric pressure increases, the boiling point will increase.
Remember, that's because the water pushes up and the atmosphere pushes down. So if I got a big arrow pushing down, I gotta heat that sucker up,
To get an equally big arrow pushing up.
which means that the boiling point will increase because now it doesn't boil at 100.
Right, don't we have to add a lot of heat to get that?
Totally, which raises the boiling point.
Correct.
Because boiling is when you get the bubbles.
Right.
And that happens at equal atmospheric vapor pressure.
Sure. And then these are very direct relationships. So as the vapor pressure decreased, which we just did on the last chart, the boiling point decreased. So if I take that atmospheric pressure and make it little,
Wait a baby one.
I don't need such a big vapor pressure to equal it.
Right.
So in other words, I can boil at a,
much lower temperature.
there you go.
Or rather, it will begin to boil as soon as the the atmospheric pressure is leaving. So this stuff might boil at room temperature. I'm telling you.
If we had a way to get atmospheric
Foreshadowing.
pressure, it is my favorite part of this unit, I got to tell you. That's
Cool.
it. So that's it. That's the whole notes, guys.
So what you really got to know how to do here is understand reference table I.
H even.
H. Yeah.
Yeah.
H. It used to be I. That's
Yeah.
why I
we need to be able to figure out the vapor pressure or the boiling points for any of those four liquids.
And the reason why this lesson seemed to be so long is because you could look at a chart and read information, but if you don't know what kilopascals, vapor pressure, boiling point are,
Yeah.
that chart doesn't mean a whole lot.
Yeah, we really needed to redefine what boiling is,
Mhm.
and then how do we use that chart? What's that dotted line mean, and how do we read it?
And so if this lecture didn't help you, go out there, look around. What is boiling?
Yeah.
How do I get something to boil at 5 degrees? How do I raise or lower the boiling point of a temperature by changing pressure? You know, you can search on this stuff, and there might be some interesting videos to see out there, but
Google vapor pressure. Google
Yeah. Check it out.
atmospheric pressure. See what you come
learn
up
for
with.
yourself if you're still confused. Because if you don't find out, then you can come tap Milks and MoNaCo, and we'll give it to you the way that we want you to understand it. But you got to do your job first. Thanks, everybody, for watching. Deuce.